When designing to survive a nuclear detonation, the assumption is that survival dictates mass. Pour enough concrete, and the radiation will eventually stop. But modern civil defense operates on strict mathematical parameters. The Swiss Federal Office for Civil Protection outlines these parameters in their definitive rulebook, the TWK 2017 manual. The prevailing civilian myth is that a safe zone requires infinitely thick, arbitrary walls of concrete extending in all directions. Reality forces a different approach. Because construction resources are finite, dimensioning a shelter is a precise exercise in mathematical subtraction, calculating exactly how little material is required to stop a lethal dose. The TWK 2017 standard approaches radiation protection as a series of specific spatial geometry problems, where material placement is more critical than raw volume. An engineer's first obstacle is the physical construction site. Shelters interact with loosely packed soil, dense rock, existing masonry, and structural concretes, materials with wildly different absorption properties. To calculate accurate shielding across this chaotic environment, engineers normalize every varied material using the concrete equivalent, or HEQ, formula. Everything is mathematically compressed to match the density of standard reinforced concrete at 2,500 kilograms per cubic meter. Once normalized, the standard sets a strict floor. The absolute minimum structural thickness for outer walls and ceilings is 300 millimeters of concrete equivalent. There is one explicit exception to this minimum. If a room is designated for sporadic occupancy, like a mechanical ventilation room or an airlock, the required thickness can be reduced by exactly 100 millimeters. This standardized HEQ value allows engineers to integrate the mass of the surrounding terrain and existing building materials into the total protective calculation. If you place a shelter completely exposed to the open air, the rules demand a massive overhead slab of 650 millimeters to stop atmospheric radiation. This chart, Figure 7, illustrates how covering the shelter with standard soil directly offsets that massive requirement. As the depth of the earth cover increases on the vertical axis, the mandatory concrete thickness plummets on the horizontal. Civil defense shelters are rarely placed under open fields. They are usually buried beneath existing urban superstructures, like apartment complexes and office buildings. Under Figure 8, the matrix calculates three overarching variables to determine the new roof thickness: the mass of the outer building walls, the ratio of windows, and the total number of concrete floors suspended above the shelter. By tracking these three metrics, the civilian architecture itself is incorporated as the primary shield, absorbing the initial radioactive sequence before it ever reaches the true roof beneath it. Designing outer walls requires accounting for radiation's behavior as a directed geometric vector with a specific point of origin. Figure 9 demonstrates calculating exposure using a 30-degree incidence angle. The surrounding dirt dictates exact line of sight exposure, creating a precise ratio, exposed area A sub S divided by total wall area A sub W. In Figure 10, plotting that exact ratio directly outputs the required concrete thickness. Creating an architectural shadow by sinking the structure into the landscape directly translates to massive material and cost savings in the final concrete pour. Moving strictly inside the complex, the problem shifts to internal access. Anterooms and internal protective doors facing the outside represent weak points for radiation to travel inward. Figure 11 introduces the Z factor, measuring internal radiation degradation. Xi marks the distance from the outer window to the inner door. The formula divides the exterior opening's area by the square of that distance. The resulting Z value maps directly to the inner wall's required thickness. Because the distance is squared in the denominator, the math forces an inverse square relationship. A minor increase in a corridor's length forces an exponential drop in the amount of concrete needed for the inner doorframe. Figure 14 synthesizes these formulas into one floor plan. Outermost wall HW1's 650 mm thickness is driven by exterior exposure. Inner wall HW2 drops to 350 mm based on Z-factor distance minus sporadic occupancy deduction. Deepest wall HW3 requires 400 mm, calculated from secondary door distance. A compliant Swiss civil defense shelter is asymmetrical by design. True protective engineering requires weaponizing empty space and environmental mass. By applying rigorous mathematical geometry, engineers ensure maximum survivability with absolute material efficiency.